Hello, my name's Arushi. My project is on creating algorithms to determine the physical properties of asteroids and applying it to measure the impact of NASA's DART mission. Thousands of asteroids are discovered every year, and currently, our rate of discovery of near-Earth asteroids outpaces our ability to analyze them. And hypothetically, if an asteroid was on collision course with the Earth, we would need to know its physical properties before deflecting it. So if there was a way that us as scientists could measure and determine the physical properties of asteroids, then we could increase our rate of analysis, and every citizen scientist could become a planetary defender. A bit of background, on September 26, 2022, the NASA's DART mission successfully impacted the Didymos binary asteroid system. Their goal was to change the orbital period of Dimorphos over Didymos, and it was successful. My project had two objectives. First, create an algorithm to determine physical properties of asteroids, and second, apply it to measure the impact of NASA's DART mission. My project had several mini objectives. For example, find the rotational period of Didymos, finding the size and the strength and the absolute magnitude of the asteroid, and then finding, in case of the Didymos system, finding how the orbital period changed post-impact, as well as doing a bit of analysis on the ejecta. In whole, my project followed a 10-step methodology, it including first observing the asteroid, and then performing differential photometry to get the magnitude of the asteroid. I then created light curves of the asteroid, and then my favorite part was analyzing it to find physical properties about the asteroid itself. To create observations of the asteroid, I used a network of telescopes located all around the world, in places like Canada, Australia, Chile, and the United States. Some of these telescopes had to write proposals to get observing time. For some, I had to get memberships. My biggest telescope that I used was the 1-meter Phelps Telescope South, but for the rest, most of the other telescopes were around 0.5 meters. I observed Didymos in 3 different stages: pre-impact, during impact, and post-impact. This allowed me to get a solid baseline of the asteroid system and see how it changed post-impact. In whole, I got over 40 hours of observations, and combined my observations with one of a few other astronomers. I fully coded my algorithm in Python and made use of libraries such as AstroPy and Matplotlib. I queried several open datasets, for example, the NASA Horizons dataset to create observing plans, and the Gaia dataset to find comparison stars. But the best part was the maths. Because I love maths, I used so many math tools like geometric mean, weighted mean, and mod, which made the project so much funner. After getting the images of the asteroid from robotic telescopes, the first step was to convert the right ascension and destination coordinates into pixel coordinates. I then created an algorithm that centered the positions of all celestial objects in my image. The next part was differential photometry. This allowed me to find the instrument magnitude of the asteroid. The challenging part was finding the right aperture size and making sure it stayed the same for both the asteroid as well as the comparison stars. I created an algorithm which found the best aperture size for each image and repeated that process for all images. I then converted the raw pixel brightness into instrument magnitude. The next part was finding comparison stars. This was essential because most of my observations were in between 2 and 4 hours, which meant across my observation, the scene conditions might change. The sky might become cloudy for a while, and the RMS is constantly changing. So to account for these changes, I needed to use comparison stars. I chose 4 to 7 comparison stars in each observation, but they had to follow a few criteria. They couldn't be variable stars, and they had to be stars with constant brightness over time. Their brightness had to also be very similar to the one of the asteroid. After finding my comparison stars, I found their instrument magnitude in each of my images. I then queried the Gaia star catalog to find their true magnitude. I subtracted the two to find the offset. I then applied that offset to the asteroid to find its true magnitude. But this wasn't enough, because even an asteroid's true magnitude can change for several reasons. For example, because their distance from us is changing, their distance from the sun is changing, or even their angle from the sun and the earth is changing. This meant that first I had to account for these changes. I applied 3 offsets: unitary distance offsets, light time correction, as well as phase offsets. This way, I was able to account for all the other changes. I applied these offsets to each of my images in each of my observations. The next step was finding composite light curves. To do so, I followed a few simple steps. First, I took an estimate of the periodicity of the light curve. In this case, it was between 2 and 5 hours. I then took 5,000 intervals between those time ranges, and for each interval, I used modulus to combine all my observations together. I then found the curve fit of the resulting light curve. I found the root mean square error of the curve fit and the true magnitude. The curve with the smallest root mean square error would be the composite light curve. I wanted to find the rotational period of the asteroid. Most asteroids are irregularly shaped, and because they do not have a big enough gravitational pull to make them spherical. This meant that while they were rotating, different amounts of light could be reflected from the asteroid. Using light curves, I could measure this change in brightness, and therefore find both the rotational period as well as its amplitude. I estimated that the rotational period was in between 2 and 5 hours. I then combined my observations and created composite light curves. The curve with the smallest root mean square error was 2.26 hours. But in binary systems, composite light curves do not only contain information about the rotation. In this case, it also contained information about the rotational period of the secondary, so Dimorphos, as well as its orbital period. This meant that if, from the original composite light curve, I subtracted the rotational period, I would be left with the rotational period of the secondary, as well as the orbital period. But here we have assumed that this asteroid system is tidally locked, which means that the orbital period of Dimorphos is equal to its rotational period. This made things so much easier. So after subtracting the rotational period from the original light curve, I repeated the process of finding composite light curves. The graph with the smallest root mean square error had a period of 11.34 hours. My algorithm produced 5 results. First, I was able to find the absolute magnitude and the size of Didymos. I found an absolute magnitude of 18.03 and a size of 850 meters. Second, I was able to measure the rotational period of Didymos. I found the rotational period to be 2.26 hours both before and both after the impact. So no change in rotational period was observed, nor was any expected. Third result, I was able to find the orbital period of Dimorphos, before and after the impact. I measured a decrease of 35 minutes in the orbital period after the impact. This shows that the DART mission had been effective at changing the orbital period of Dimorphos. Fourth, I measured the ejecta coming right out of Dimorphos right after the impact. I saw the ejecta had a length of over 15,000 kilometers, which meant Dimorphos was likely rubble. Fifth, I measured the magnitude of Didymos before and after the impact and compared it to its predicted value from the NASA Horizon dataset. For impact, the values I was getting was very close to the predicted magnitude. But post-impact, I noticed an increase of 1.3 magnitude after the impact. Around a month later, it went back to its normal rates. I was also able to find the asteroid composition, because it is assumed that if the rotational period of an asteroid is less than 2.2 hours, it's monolithic, means that it's formed by one single rock. This is because if it was rubble-based, it would have flown apart with this much speed. But if the rotational period of the asteroid is above 2.2 hours, then it's assumed to be rubble-based, as long as it has a diameter of above 150 meters. In this case, I measured the diameter of Didymos to be 850 meters, and I measured its rotational period to be 2.26 hours, so above 2.2 hours. This meant that Didymos was rubble-based. All of my results validated with other sources such as NASA and the Atlas database. In conclusion, this shows that my algorithm was effective in measuring the physical properties of asteroids. I was able to find an absolute magnitude of 18.03. I was able to find a diameter of 850 meters. I was able to find a rotational period of 2.26 hours, and I was able to find an orbital period of 11 hours and 55 minutes before the impact and 11 hours and 20 minutes after the impact. I was also able to determine that the asteroid was likely rubble-based. I was also able to analyze the ejecta coming out of Didymos. My algorithm can be used by citizen scientists all around the world to measure the physical properties of any asteroid. My project took almost a year to complete, and I faced a few errors and limitations in my algorithm. One of the errors is that in November of 2022, the asteroid moved into a very crowded star field, which meant the accuracy of my observations went down, since stars were always passing in front of the asteroid. One of the limitations is that most of the telescopes I was using had an aperture of around 0.5 meters or less. And since I was aiming to get a signal-to-noise ratio of above 100 at all times, this sometimes meant increasing the exposure time of my observations a lot. This led to me getting less images per observations. I've submitted all my observations on AlgDef, and I have posted my code on GitHub as a training module, so that anyone else can replicate what I've done. In the future, I would like to provide citizen-side support to the Hera mission, which will be measuring the impact of NASA's DART mission in 2026. Thank you to everyone who helped me during my project by giving me observing time on telescopes, helping me when I had queries, and giving me feedback along the way. Thank you.